So this is a very different type of presentation. Over the past, say, 5 years, RTEMS has been working on having pluggable schedulers and symmetric multiprocessing support. Last year, I gave a presentation on what was planned, where things were, and some challenges, which if somebody wants to talk offline, we can go over the kind of things you're going to face as problems moving into SMP applications from Unicore. This is it. So this has been a very busy year. This is the culmination. We actually held off a release because we thought we could go from marking SMP as experimental to production. So this is near production. Flight code has been run on it, and the Gaia flight code, the ESA Gaia flight code has been run on it, and the ESA Proba code has been run on it. There's a commercial application about to be fielded, and this is a combination of work, just so I can just claim it up front. Canada Space Agency has paid for some of it, ESA's paid for some of it, commercial people have paid for some of it, and there's a fair amount of, at least some work by students along the way. So really, here it's basically what we've done over the past year. Right now we have SMP on the Spark, Leon 3, Leon 4 next generation microprocessor, PowerPC QRIQ, ARM, ARM Zynq, and x86. The PowerPC, I saw email this week, somebody is committed to bringing it up on a 24-core QRIQ PowerPC. There's a student at York working on a port to the Epiphany, the Parallella, which is called an MANY mini core, and that I think some of their configurations are 64 and 128 cores. So with the pluggable scheduler, this allows us hopefully to adapt, still keep our we kept our uniprocessor performance, and it allows us to have SMP schedulers and to have schedulers that adapt and scale. So the emphasis on all of this has been on performance and sound theoretical foundation, and I'm really thrilled with everything that's happened. SMP sounded really simple even a year ago to finish up, and when we got to working on it, we realized that it's a long, long thread to pull, because it's not enough just to switch threads and schedule them on multi-core. All the libraries actually have to be SMP safe too. So once you start on that, you start fixing file system layers, locks and support libraries, the C++ atomic support, because now C++ 11 and C90, I think C99 even has atomic instruction support built into the language, so we ended up working with Aeroflex Geisler to get some of that fixed. We worked with the GCC community. It turns out that everybody's favorite per task variable feature is actually utterly, completely, and semantically broken on SMP, so if you want to use it, quit. Just quit doing it now and move away from it. We disable it in SMP, and I'll tell you VxWorks does the same thing. So we added a bunch of new SMP tests, and we did an untold number of patches upstream to GCC and NewLib. And this is kind of really at the nerdy technical levels, but I'm going to try to go fast because I'm between you and dinner. The first thing that got added, the first thing that was a big feature was thread affinity. So thread affinity is specifying which cores in a system you want your thread to be allowed to run on. And it's a good feature. It allows you to keep your locality of reference, manage your cache effects, and migration. But the scheduler's got to be aware of it, honor it, and it requires APIs to manipulate what are called CPU sets, which define where you can run. It's a lot like a signal mask in POSIX, and you've got to be able to dynamically alter it. And the burden is now on you when you use this to avoid priority inversions and ensure schedulability, and make sure that you don't do something like I had in the earlier talk where you accidentally do something and suddenly every thread in the system migrates. There are rules for doing it, and there's papers on how to assign CPU sets. So in typical RTEMS fashion, we desperately try not to avoid inventing new APIs when there's practice. So we have a Linux-compatible CPU set API with the missing functions from the BSD world. So this is essentially the same. They're similar to the operations on signal masks where you clear them, you add CPUs, you can OR them, AND them, XOR them. There's a lot of APIs. Right now, the basic default set size is 32 cores. So this is a bunch of basically wrappers to add and manipulate a bit mask of which cores you're allowed to work on. So you set a bit, and set a bit in the CPU set to specify you're allowed to run there, and you clear it to specify that you're not allowed to run there. This we added because a lot of people run without the POSIX API. We added two methods to the classic API. These should look a lot like any other call that starts with RTEMS. So we added get affinity and set affinity. And obviously if you change affinity and I say now you're not supposed to run on core 0, you're supposed to run on core 1, if you're actually running, you're going to move. You're going to quit running on 0 because you've changed the set of CPUs, the set of cores it runs on. Remember, we're dealing with a system that's got more than one processor in it, and we're trying to figure out the magic balance of threads across the system. As normally things are, POSIX takes more APIs to get some of the same things done, and mainly in this case it's because the CPU set, the thread affinity, got added to the POSIX thread attribute set. So this propagated up into the C library. If you notice, they have NP on the end of the method. That's the POSIX nomenclature for a non-portable method. These look a lot like the Linux and the BSD APIs. The big difference between Linux and BSD is, and I don't remember which is which, one calls it CPU set underbar T and the other calls it CPU underbar set underbar T. And they've been arguing about this for over a decade, and it's not in POSIX. I don't know when it'll be, and I disclaim it totally. It's an argument over an underbar and some other names. So basically, you can specify the affinity when you create a thread, and you can change it on the fly with the get and set affinity. While we were doing this, it turns out POSIX never defined a method to actually dynamically get the attributes of a thread. So while we were here, we added this anyway, so that got done. That's just another example of how you kept pulling on the thread and more work kept popping up that you hadn't planned on. No point of going too far into this except that when you create a thread now in the classic API, this is for 0 to the number of cores, 0 to n, and after you create the task, but before we started in the classic API, we zero out a CPU set and set the bit for the core that this thread's allowed to run on, and then we set the affinity and start the thread so that thread will run on that core. So that's what that example I had earlier did. So we loop through and we create a thread for each core. It's pretty arbitrary. And there's some rules about priority and the trick is non-overlapping CPU sets. If the Gaia example earlier locked each thread that was locked one thread to a core, so it never migrated. And they've got hours, I think they've got days of trace data that shows it never migrated. So we've got 3 SMP schedulers now. We've got one that is a regular deterministic priority, constant time execution that does not support affinity. We've got one that supports affinity, just a couple of plugins based off of the same core API. And we still have one, if anybody remembers this, we have a class of schedulers we call simple, which is back to your modules things. Sometimes you want the same functionality, but you want it to be algorithmically very simple and low on memory. So we have a linear list of threads on a system with low memory usage. The other cool thing RTEMS got along the way, which is pretty modern in the research world, we have something called clustered scheduling. The first thing we all think about is there's a single instance of a thread scheduler, and it sees the whole system like this. I mean, this is very much how the Leon is. It's multiple instances of single cores, a big shared bus, RAMs on the other side of it. That's really what it is. So what happens is you've got one scheduler, and whether you have or don't have affinity, the single scheduler has the ability to manage and move threads back and forth across those based on whatever settings you use. But there's a concept, you can use affinity, or you can use this really cool concept called clustered scheduling. So what you end up with is multiple thread scheduler instances. So you can say that one core 0 is running a regular old single processor uniprocessor scheduler, and the other 3 cores are running an SMP scheduler. So what does that let you do? It allows you to do schedulability analysis on the single core scheduler using classic old school known tried and true scheduler algorithms, and you can use the SMP on the other because there's still a lot of problems in schedulability analysis left in the SMP world. And a lot of the presentation that's left that I am blowing through as fast as I can, so there should be a bunch of questions because this is actually pretty hard conceptual stuff. What this allows you to do is group sets of related threads so you can lessen cache effects, you can share resources, you can reduce your complexity, your schedulability analysis, and one of the things Spacebell emphasized that I had forgotten is you can leave a core idle and you can do things which effectively allow you to insert technology and capabilities later and not impact the schedulability analysis you've done before. So that's a really good one. And the other thing, mentioning user there, this is kind of greenfield territory for us all, and how do you best utilize these, and how can you mess up and really screw up going to this too, because so if anybody learns patterns, please share them, because we're collecting them, and hopefully we'll get some best practices out even beyond the RTEMS community. So really, this is what you want. This is hard, deep, embedded real-time, and you want really good control. So this is what this is doing. So what do you get with a clustered scheduler? The same stereotypical of simple SMP system. Okay, we got no affinity, and now we got affinity. We can run 2 instances of the scheduler. And it allows you to avoid migrating threads across the 2, but it's still one application, and data can be shared. So you can keep things from moving. And there's I've got some real examples of why you might do this. Now the complexity comes in because now you've got multiple schedulers, and so a thread is associated with a single scheduler at a time. So you can move it from, in that other example, the first 2 cores to the other 2 cores. So you can get the scheduler and set the scheduler, and again, you can obtain the cores associated with a particular scheduler. So we are out on our own here, but this is kind of new stuff. This is a very ugly slide, and I'm just going to say that when you configure a system like this, it kind of looks like the regular RTEMS scheduling, except it's like more complicated, because basically you're associating a scheduler instance with each core. The schedulers have names, and it'll be in the manual much better than that. So the example here is the code to move a thread to another scheduler. So it's the same kind of scheduler that was system, I think, that was configured on the previous slide. So we've got a quad-core system, 2 scheduler instances, and it's configured as 2 dual-core schedulers. So during RTEMS initialization, all the schedulers are initialized, and the idle threads are created, and they go to their threads. And also during RTEMS initialization, normally you create 1 user initialization thread, and it will start on the default scheduler, and all of the schedulers start assigning cores based from the highest number to the lowest number, so it's going to run on core 1. We're going to create a task, and whatever the other arguments are, we're going to get a task ID, but remember, RTEMS does, the classic API creates and starts execution as 2 operations, unlike pthreads. So we can get the name of the first scheduler, scheduler 1, the second scheduler, and we can set the scheduler for this new thread to the second scheduler instance, the one with affinity. So TA1 is now inside the other scheduler. So the init task can only run on core 0 or 1, and the TA1 can only run on cores 2 or 3. So we've already got some locality by design, which is quite handy. So ripping off some nice architecture pictures that I didn't draw, we can now layer some system configurations onto these for various reasons. So the Leon 3 and Leon 4, next generation microprocessor, whatever they're called, are all basically kind of the same rough architecture. They're multiple instances of single processor cores with a cache, an FPU, an MMU, and then attached to a bus. So there's not a lot of shared resources here other than the RAM and the peripherals and the bus. So you got to worry about things like cache coherence and how much are you fighting over the same data. So really what we might want to do is, let's say all our I/O and all our high priority critical task set, I think is the word in rate monotonic scheduling, the critical tasks that we want to do schedulability analysis. So for simplicity, we could direct all the interrupts and put all the low-level I/O tasks and a critical task set here on core 0, and that is a classic uniprocessor system you could do rate monotonic analysis on. So we have kept the analysis back into the old school world in simplicity. And simple is good in embedded systems. We could put another set of critical tasks here if we wanted to. I guess I actually meant we could do strictly I/O and interrupts, and we could do critical tasks, and these are uniprocessor priority schedulers. And then the other two, we could just use as background, just to let background work happen on them. So this way we have basically allocated two to background work tasks, one and two to special purposes. So what we really did in this layout was we focused on schedulability and system predictability, because now we know that all interrupts are going to a single core, so we don't have any contention on interrupts, and we don't have any contention on device I/O. We made things a lot simpler to think about. So I learned this week that I thought this was one of the worst examples of an architecture possible, but apparently the QRIQ is also very much like this. When you look at the QRIQ architecture, which I don't do one in here, you can see, looking at the silicon, that it's multiple instances of quad cores. But it turns out that, does anybody notice what's magical about this and should drive you crazy in space software? See if I'm moving right. Is that the right? There's a mouse somewhere. AMD's architecture is multiple what they call modules. They're two integer cores on a module with one floating point unit. This suddenly sounds really bad, doesn't it? So this is a resource beyond just memory contention now. And the QRIQ, I think the 24 core actually has 24 integer cores and 12 floating point units. So we have a serious issue that if you're doing floating point math and you misdistribute your threads, you're going to end up with half the system performance that you expect, which is not a good thing. So the clustered scheduling and affinity come in handy. So one simple way to do it is to do an SMP priority affinity scheduler. You could do one instance. This is one way to do it. And then basically put all your floating point threads, since RTEMS lets you specify whether a task is floating point or not, you could put all your floating point threads associated with core 0, so that way you get full utilization and no conflict on the floating point unit. So you can, and that's a way to balance it out. So this at least allows you to take it to account for that. But the thing that I don't like about this is that we've never had to consider the physical architecture of a processor in laying out and scheduling threads nearly as much. So now here we've got an architecture which, if you don't take this into account, you have a really good chance of not getting anywhere near the performance you think you're going to. So the goal of this one is we use the clustered scheduling, we used a single scheduler instance and affinity to eliminate contention on the FPU, but we didn't address cache effects and locality, which is the other bad thing in SMP systems, because if you start hammering all the data from different cores, what you end up doing is have to do the cache coherence. I don't think I'm moving a mouse, but if you look, there it is. Notice each integer core has a level 1 cache, each module has a level 2 cache, and although it doesn't appear this way, this is basically one level 3 cache out here. So the more the 2-core and the 1-core modules access the same memory, the cache coherence is going to start thrashing the bus. So, and this is why you see benchmarks where things start falling apart on SMP because of data contention and cache effects. So here's another example. So it's the same basic architecture, but just a different idea. So let's just do it as a cluster of 4 scheduler instances with one SMP priority affinity scheduler instance per block. We can still do the same trick with the floating point. So now what we've done is hopefully we have some natural locality in our reference in our application, and we can dedicate tasks to each one of these 2-core modules in a way where they're hitting the level 1 and level 2 caches more and not hammering the level 3 cache nearly as hard. And so hopefully we can get much higher throughput out of our system. In this, we managed to avoid contention on the cache and the floating point units. So that kind of makes sense, because this is the architectures get ugly and the problems get harder. So you can do something and get near full performance out of a quad core, and you can do the same thing wrong and you can get half the performance you did on a uniprocessor. So you really got to be thinking about the things that we were always supposed to think about, like locality of reference, or do you fit in the cache, those type of things. Now they've become a little more important. And unfortunately, from my perspective, you can draw a box around the OS, and that's a problem space and you can solve it. We can draw a box around the language runtime, and that's a problem that we can solve it. And then each one of you is going to bring a new application with, just like our support libraries where we had issues in each one of them along the way, you're going to bring application code which has new and interesting problems. And as we go through this, I'm loving to hear what the new and interesting problems are. So it turns out when you're doing clustered scheduling, Alan Burns and Andy Wellings, who have done a lot of great real-time work at the University of York, came up with an extension essentially of the priority ceiling protocol, which works across schedulers, because with the multiple scheduler instances, now you could have threads at different priority. So basically it allows you to specify a priority per scheduler instance, so when you get the lock, you're at the right priority on the instance. If you notice, this is actually quite recent. So I blew through this, and I didn't say two things I wanted to say. The last final bit of work was sponsored by ESA. That's what got us and a commercial user on the ARMS Inc. The ESA work was for the next generation microprocessor, which in the US is mostly better known as a Leon 4. There's been work by a lot of people, including a Google Summer Code student, Gader Bloom, who was on the contacts, the first slide. I didn't give him credit. There's been a lot of work by Embedded Brains, Sebastian Huber, who one of the West Virginia guys mentioned is giving him QEMU patches yesterday. There are a lot of people who've contributed to this. The Gaia flight code is like a star astronomy. I think it's called the billion picture map or something of the galaxy is what their goal is. They took their flight code and moved it to a dual-core 712 and got a 1.8 speed up. They're still in the process of trying to speed it up on a quad-core. Last I knew they were at 2.8, and they had a data stall in their own application, 2.8 times the throughput of the single core. The thing we're learning, and I didn't put a slide on it, but Amelie wanted me to mention this. A lot of you guys, I've heard the term rate jobs used in reference in JPL presentations before, where you have one thread that runs everything that has to happen every 50 hertz. And so you'll go down and do the 10 things in a linear list. That inherently serializes it, and that's one of the things the Gaia code had going on, was how do we break all these uniprocessor assumptions where it really didn't matter that you had 15 things you did every 50 hertz. They were going to happen linearly anyway, so it didn't really matter if it was one thread or 15. Now you have that inherently serialized that application, and I think that's what they're at the point of battling, that kind of issue now. There are a lot of challenges. The other application was the Proba, and I don't really know as much about how much they're done. I don't think they're quite done yet, but there's a dual-core mission from ESA as a technology proof that's scheduled. It's actually on the schedule and funded, so there should be a proof of concept, and everybody likes their technology proof missions. I guess ST5 was our big one at NASA, and one of the earlier Proba missions was our big proof of concept mission about a decade ago also with ESA. This will be, I guess, the SMP proof of concept mission for ESA, and hopefully NASA won't have to fly one. Maybe they'll look and see what happened at ESA. But this is a huge community effort. It's a combination of every community involved in RTEMS to make something happen. This was a big, big effort, and I will be the first to admit I horribly underestimated how much work it would take. Even down into the 6 months before we were done, I was still misestimating the amount of effort. But it's in very good shape. It's high academic based on, Burns and Welling are top in the field, and that's a recent development. The clustered scheduling is a recent schedule thing. So hopefully we're laying the foundation for you guys to get the provable, predictable systems you need as you move into SMP. But it's kind of a brave new world for everybody. So that's what I've got. So that was a hard one to end the day with. I should have taken it to him. I could have.
So, one general question. What is the difference, if you have evaluated, between using the clustering affinity and AMP or TSP solution, which in my view are similar resolve a similar problem.
Okay, the AMP, you have different operating system instances, so there is no, any shared data is explicit in the single OS is not able to mute, like lock data. In a clustered solution, a regular mutex works across the clustered boundaries. So if you at runtime decided you needed to move a thread from the scheduler instance 1 to the second scheduler instance, you can do that. You would have to, with a single call. If you did that with AMP, you would have to move, you would have to build in some kind of like failover mechanism in your application. So it is similar in a way to AMP, except you get one scheduler and one application. You get one application image and one OS image that can handle the concurrency. And I don't, what's TMP?
TSP, time and space partition.
Yeah, it's, you're still getting the times partition, but you're not getting the space partitioning. And you can use different algorithms. Most of the time, like ARINC, all you're doing is manually time slicing the two partitions and on a fixed schedule.
I mean, normally if you use an hypervisor and you allocate, you make partition allocating different CPUs for
Right.
partition, you might achieve similar solutions.
Right, but the data sharing between the partitions, in that case, if they were that separate, would be harder.
But you use,
You'd have to use like
and whatever.
Right. Yeah. It's just a different space.
It looked like the mapping of schedulers to cores is something that's done at compile time. Are
Yeah.
they fixed there, or just to totally blow our minds, can the schedulers migrate around?
It's a good question. I guess if somebody wanted it, yeah, I guess they could change, but at the moment they're fixed. Because the intention's that's to help your schedulability analysis. And
Failure mode, though. That could be a failure.
yeah, it could. And you know, I only showed using normal priority schedulers. I mean, we've also got earliest deadline first. So you can go back to the comment on the first day. I mean, you could schedule earliest deadline first in one of the partitions if you wanted, one of the clustered partitions if you wanted to.
Other questions? Okay, thank you, Bill. Okay, you guys, you are really the stars.